Welcome back. After discussing the back surface field, the PERC, the TOPCon and the heterojunction solar cells, we will discuss some interesting contact architectures. The first interesting cell concept, which is commercialized by SunPower, is the interdigitated back contacts IBC solar cell. The principle of the interdigitated back contact concept is that it does not suffer from shading loss of a front metal contact grid. All the contacts responsible for collecting of charge carriers at the N and the P side are positioned at the back of the crystalline silicon solar cell. An advantage of these interdigitated concepts are that you are able to use monocrystalline float zone N-type wafers. An interdigitated back contact is lacking one large PN junction. Instead, the cell has many localized junctions. The holes are separated at a junction of P plus and the N-type silicon, whereas the electrons are collected using an M plus type silicon. The semiconductor metal interface is kept as small as possible to reduce the unwelcome recombination at this defect-rich interface. Another advantage is that the cross-section of the metal fingers can be made much larger to reduce the resistive losses of the contacts as much as possible. The fact that the contacts do not cause any shading losses at the back allows them to become larger. The passivation layer can have a low refractive index such that it operates like a backside mirror. It will reflect the light above 900 nanometers, which is not absorbed during the first pass through the solar cell, back into the absorber layer, enhancing the absorption path length. From the back side, an interdigitated back contact solar cell would look like this. At the back, you have two metal grids. One collects the current of the N-type contacts and the other collects the current of the P-type contacts. At the front side, the losses of the light-excited charge carriers due to the surface recombination is suppressed by using the same tricks like the back surface field as discussed for the rear surface for solar cells based on P-type wafers. The surface recombination velocity on the front surface is determined by the minority charge carriers, in this case, the holes. Consequently, we have to create a front surface field. A higher N-dope region is placed at the front indicated by N+. The interface between the higher doped N region and the lower doped N region acts again like a PN junction. In this case, it will act as a barrier for the light-excited minority holes in the lower doped region to diffuse to the front surface. The front surface field behaves like a passivation of the defects at the front interface and allows to have higher levels for the hole minority densities in the p-doped bulk. At the front side, the reflective losses can be reduced using the same tricks as discussed for the Pearl solar cell. Deposition of a double layer at the reflection coating and texturing of the front surfaces. SunPower is the company that has developed and commercialized a cell technology based on the interdigitated back contacts. As I already discussed with the crystalline silicon heterojunction solar cell technology, that you can make an architecture in which both at the front and at the back side you place a metal contact grid. This allows light incident from both the front and the back to be absorbed in the PV active layers, increasing the cell's performance. This architecture is referred to as bifacial. Normal solar cells, including a non-transparent backsheet, are referred to as monofacial. The last concept I will discuss is the metal wrap-through cell architecture. For a solar module based on standard crystalline silicon solar cells, the individual wafers that form the cells are connected in series by connecting the front metallization grid of one cell to the back contact of the next cell. This process is called contact tabbing. It's a time-consuming and precise processing step that in the past was frequently done by hand. A consequence of these interconnections is that the cells cannot be placed directly side by side, but that spacing is needed between the cells. This area is accounted as loss when looking at the aperture area of a solar module. The metal wrap-through technology, in literature often abbreviated to MWT, prevents this loss in the module area as it wraps the metal front contact through the base of each cell using a so-called via and places both front and back contact side by side on the backside of the cells. In this way, the electrons collected by the front emitter are transported to the back of the solar cell. Evidently, care must be taken that the via does not create a short circuit. Individual cells can now be placed much closer to each other. This image shows the Sunweb technology. It was demonstrated some years ago by Schott Solar and Solant Solar. This technology can be recognized by its very special front contact design. The metal fingers are surrounding the wrapped-through contacts in a very distinctive, almost flower-like pattern. Also shown is the back conductive sheet that collects the currents of the p-type and the n-type contacts. Summarized, we have discussed the design principles for the various crystalline silicon-based cell architectures like the back surface field, the Pearl and the PERC, the TOPCon and heterojunction solar cells. We also discussed contact architectures like the interdigitated back contact, bifacial and the metal wrap-through. Over here we give an overview of the achieved conversion efficiencies under standard test conditions in the lab. Note that the moment that I have recorded these lectures, these numbers might be already outdated again. So please check yourself on the latest record numbers. The back surface conversion efficiencies are in the order of 20%, and the PERC solar cells have efficiencies in the order of 25%. Fraunhofer ISA has demonstrated record efficiency for the TOPCon concept, 25.8% using a N-type wafer and 26.0% for using a P-type wafer. LONGi has demonstrated the current record efficiencies for the heterojunction solar cell. 26.3% for a monofacial front contacted cell and 26.81% for the interdigitated back contacted cell. This is the current world record for crystalline silicon-based solar cells under standard test conditions. Here we're talking about solar cells. In the next video, we are discussing how modules are being made out of these individual solar cells. So, see you in the next video.